I'm Patrick Alvarez. This is Alexander George and Brian Gleason. This is our project, the Power Transmission Design System.
We were tasked with designing a transmission system entirely out of commercially available components. We chose to source our components from Boston Gear, and upon completion of our design, we checked the validity of Boston Gear's rating system using the AGMA design criteria.
We have our design requirements, which are to transmit 8 horsepower through the entire transmission system. Input shaft speed is 1600 RPMs, output shaft speed is 80 RPMs, which means roughly 500 foot-pounds of torque at 8 horsepower. And the output shaft must be rotating in an opposite sense relative to that of the input shaft.
The materials we used for our design was the Boston Rotary Drive Product Catalog, or the Boston Gear Catalog. This was used to determine our gears and bearings. We used MatWeb, material database, to choose the hardness factor for our materials. And we used our textbook, the Shigley's Mechanical Engineering Design, to choose, to find our equations we used for our AGMA design criteria, and the equations for the shafts, gears, and bearings.
Our original conceptual design was designed with 9 gears. It ended up being unexpectedly large due to the way we designed it having a single path for the power to transmit through. And due to this single path, each gear must be rated to operate with the entire 8 horsepower at their operating speed, which means each gear, as you get through the system, the torques get higher and higher.
For our final design, we chose to divide the power as it entered the transmission. By doing this, we had the power travel along 2 separate paths, half in each one. This allowed us to use smaller, lighter, cheaper, and more easily available components, as each one only had to be rated to hold 4 horsepower at its given speed rather than 8. In addition, we designed the final system to have all of the bearings located in the same plane, so that they would simply be sandwiched between the 2 halves of the casing, which would simplify both assembly and disassembly and reassembly for maintenance purposes. And you can see the power enters the transmission at this point here. By placing the pinion on this side of the bevel gears, we were able to both reduce the overall length of the transmission and eliminate a counter gear that would be required between these spur gears to reduce the direction of rotation from input to output. After the initial reduction and division of power here, the power travels along these shafts out to this pair of spur gears for an additional stage of reduction, before being transferred back into the final stage of reduction, where the power is rejoined together at the output bevel gear.
This is our deflection analysis. Due to the way the bevel gears split up and rejoin at the end, the input and output shafts do not vertically deflect. They only reflect in the rotational direction. This picture is the deflection for shaft EF, which connects gear E and F. The maximum displacement is only 0.03 millimeters. This is the shaft connecting gears B and C, which is towards the beginning of the transmission. The maximum displacement here is 0.08 millimeters, which is mainly due to its cantilever setup.
Our bearings we chose to source from Boston Gear rather than from Timken, as we felt that Boston Gear's catalog was easier to use, and also because we felt that by sourcing the bearings from the same manufacturer as the gears, the criteria used to rate them for their given power would be consistent with the powers given for the gears. The 3 types of bearings used are 1630, 1635, and 1641. All 3 of those are regular single groove radial ball bearings. We didn't use any thrust bearings anywhere throughout the transmission, as none of the thrust loads were high enough to warrant it.
After we selected our gears, we had to do the AGMA design criterion. The factor of safeties for both bending and wear had to be higher than 1, and all gears exhibited a factor of safety higher than 1. Gear C had the lowest factor of safety, which was at 1.04, and that's because the highest amount of contact wear is going through gear C. As Alex described before about the reductions, the bevel gears here on the input shafts show reduction of 3 to 1. Reduction between the spur gears are 2.22 to 1, and reduction between the last final bevel gears are 3 to 1.
This is our real-life application. We chose to take advantage of the high-speed, low-torque to low-speed, high-torque conversion and design a kettle which would be mixing high-viscosity materials such as silicone in the pharmaceutical industry.
In conclusion, our team successfully designed the transmission system. We used what we learned in Mechanical Design 1 and 2 to fully complete the design. And then if we were to redo this project, we would first ask for more gear catalogs, and then as we're designing the shaft, the transmission system, we would want to start with the final gear and work our way back to the input gear.